Okay, so here comes that very, very unsteady ground that you kind of have to work through when it comes to section 6-2, and it comes to simplifying radical expressions. We got pretty good at simplifying radical expressions when they were square roots. Take a look at that square root of 24, right? That square root of 24 could be factored into 4 times 6, and the reason why that 4 is red is because it's a perfect square, right? And we can take the square root of that 4, call it 2, and then we still have that 6 left over. Understand something here, that this also can extend to other roots besides square roots, like cube roots. But we do not look for perfect squares when we split apart 24. See how when it came to 24, when it was a square root, it made sense to split it apart into 4 times 6 because 4 is perfect square. 4 would not make a lot of sense here with cube roots because 4 is not a perfect cube. However, 8 is actually a perfect cube, and so it would make sense to factor 24 into 8 times 3, and that would allow us to take the cube root of 8, which would put it as 2, and then our leftover radicals left over would be the cube root of 3. Okay? So this leads to a very, very important concept that I hope many of you have your pencils ready and you're going to write this down. And that would be a list of not just perfect squares. You guys know your list of perfect squares. But how about a list of perfect cubes? So let's generate that list, shall we? Well, the first perfect cube would come from us taking 2 and raising it to the third power. So the first perfect cube that we're really going to work with here a whole heck of a lot would be 8, right? The next one would be 3 to the third power. What's 3 to the third power? 3 times 3 times 3. That'd be 27, followed by 4 to the third power, which would be 64. 5 to the third power, I think that's 125, right? Continue. Let's do just one more. 6 to the third power would be 216, and then this pattern can continue and continue. So when we're starting to simplify, say, cube roots, we are looking for perfect cubes to factor, not necessarily perfect squares. See how this perfect cube list gets used in this example right here in problem 2. What's the simplest form of the cube root of 54 times x to the 5th? Let's be careful here. We do a little bit of highlighting. Now, if it were me, seeing how all this textbook kind of tries to muddy the waters here a little bit, what I would highly suggest you do on this problem would have been split this apart and look at this as the cube root of 54 times the cube root of x to the 5th. Now I'm going to set that cube root of x to the 5th aside for now, and let's just focus on that cube root of 54. 54 is not a perfect cube. You look at that list right there, it's not on that list. But is there a list that's from that? Is there a number from that list that could divide evenly into 54? Yes, there is. It's 27, isn't it? Right? So couldn't we split apart 54 into 27 times 2? And so then wouldn't that allow us to take that cube root of 27 times the cube root of 2, and we could look at that. Sorry, I'm making a mess here, but it would be the cube root of 27 times the cube root of 2, which would then just lead us to 3 cube roots of 2. Okay, so that would be a part of it. In fact, you actually can see that part of it. Let me grab a highlighter. 3 cube roots of 2. See that final answer? There's the 3. And then there's the cube root of 2 part. The stuff you see with the x's is what was actually going on. Let me grab a highlighter. The stuff you see here with the x's is actually what's going on right here. I'm going to try and give you a very simple trick here. Many students in previous years struggle with this trick, but honestly, it's not necessarily a trick, it's just a fact that's just true about any type of root. When you look at that cube root of x to the 5th, there is nothing against the rules about me splitting this apart into something that looks like this. A cube root of, say, x to the 3rd times x squared, right? Remember our property of exponents, that 3 and that 2, when we add those together, that would create that 5 right there. And what that allows us to do is, doesn't that allow us to now take the cube root of x to the 3rd and multiply that by the cube root of x squared. Oops, let me clean that up. Of x squared. So then that square root of, sorry, the cube root of x to the third would just be that x you see right there. And then over here you see that cube root of x squared is still right there, that cube root of x squared. And we'll clean this up here in a minute. Let me show you how we kind of roll through these problems here, to make it not look as messy, because I definitely wrote all over the place here. So rather than have you guys do this problem on your own, we're going to do this one together. See how I still have that list of perfect cubes over there on the side? We're going to need that. Okay, so they want us to find the simplest form of the cube root of 128x to the 7th. Okay, so please, 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 please keep this in mind, that we are going to still use this property from right up here. The nth root of two numbers multiplied together, we can split it apart into two nth roots. So that's exactly what we're going to do here first on this problem. Let's split this apart, and let's think of this as the cube root of 128 times the cube root of x to the 7th. Now let's just focus specifically on that cube root of 128. Of course, 128 is not on this list, but is there a number that's on that list and you want the biggest one that will divide evenly into 128? I think 64 can do it, right? 64 times 2 would give you 128, right? And then we can simplify that. Now, let's see where we go next. I can't remember where I go next with this. Let's go look at the next one here. So we'll simplify that cube root of 64 times 2 here in a moment. But if I have to try and break apart the cube root of x to the 7th, here's the trick. A lot of students think this is a trick, but it's really not that tricky. Think back to the last unit and how easy it was. Let me do a little bit of writing here. How easy was it when I asked you to do this, guys? A square root of, say, x to the 8th. Because that's an even and that's an even, pretty much your answer was x to the 4th. Let's do another one. How about a cube root of x to the 12th? That was an easy one because 12 divided by 3, you'd get 4. So notice your answers that you get each time that you do any type of a root where these two numbers here are divisible. It was super easy to do because the answer was an integer. Well, do you notice that if we tried to do the same thing with the 7 and the 3, we would not get an integer? So we want to split it up into two factors. X to the 7th split up into two factors where we can do this type of move. Okay? So the trick is to split x to the 7th up into two factors where we actually can take the cube root and just simply take the exponent and divide it by that index there of 3. Now take a look at what the correct answer is. Go ahead and write this one in. X to the 6th times x to the 1st. Okay? Allow me to explain why you don't do this. X to the 3rd times x to the 4th. You don't do x to the 3rd times x to the 4th for the same reason why when we were dealing with this problem right here, remember square roots, and we were doing the square root of 32, we didn't want you to do this, 4 times 8. The reason why is because, sure, 4 is a perfect square, but do you realize there is also another perfect square that would go into that remaining number right there? So the trick is to find the biggest perfect square that would go into that number that's right there. The biggest perfect square would be 16. We want the biggest perfect cube that would go into x to the 7th, and the biggest perfect cube would be x to the 6th, not x to the 3rd. So when it comes to any type of advice I can give you on these problems, is to make sure that when you are looking at this exponent right here and looking at that number right there, find the highest number that would be actually still divisible by that number right there. In a lot of cases, and I mean a lot of cases, wink wink, nudge nudge, when you're dealing with these problems, ladies and gentlemen, this is one thing I'm going to tell you right now that can make life a lot easier for you on these problems. A lot of times these types of problems really break down into just one less than the exponent that you're looking at there. For example, if that's a 7, 6 and a 1 is what you're going to be aiming for right there. In a lot of cases, that's what ends up happening quite regularly. So to wrap up this problem, let's now go ahead and take all this apart here. So back over here, we had the cube root of 64 times 2. Let's take the cube root of 64. Wouldn't that be 4? And then we still have that cube root of 2 that's still left over. Keep that multiply sign. the cube root of x to the 6th, just like from the last lesson that we did. That's pretty straightforward. That would be x squared. And now, because we have x to the 1st, let's just write that as simply the cube root of just x. Now, to write your final answer, look at this final answer and how that gets made here. It's really not that tricky. Take a look at what's not an irradical, a 4 and an x squared. Just keep that outside the radicals. Okay? And then the stuff that's still inside the radicals, go ahead and multiply those together, which gives us that guy right there. Okay? Not too bad. I'm kind of debating on whether or not to go through a couple more examples here on just this video here, but trust me, when we go to the next video on the next problem, we're going to be practicing this quite a bit more. So as we look at problem number 3, let's take a look at how we can work on this concept a little bit more.